So, hello everyone, and a very warm welcome to today's quantum leadership session on photonic quantum technologies. My name is Mila Kurunovska. I'm the marketing and event manager at QBN, and I'm delighted to be your moderator for this insightful session. It's wonderful to see many of you joining us live on Zoom and YouTube from across really the wide quantum ecosystem. And whether you're a long-time QBN member or a newcomer to the community, welcome. So today's session is all about photonic quantum technologies, which is an exciting field that explores how light can be used to advance quantum computing, communication, and sensing. Photonics offers unique advantages such as speed, low energy consumption, and scalability, and it's really playing a growing role in making quantum technologies more practical and simply accessible. So we'll explore this topic through three unique lenses, thanks to a fantastic lineup of QBN members that we are having today. The first one is Benjamin Chicos from Photonics, who will start us off by talking about scalable quantum computing with photons, the power of continuous variables. And then we'll hear from Professor Dr. Thomas Foltz from Quandela, who will speak on accelerating innovation and shaping industrial advantage with photonic quantum computers. Last but not least, we'll hear from Roberto Siagri, who is the CEO of Photonium, and he will introduce us to the multidimensional qubit or qudit with photons, an approach that goes beyond the binary model of quantum information. So each of these talks will offer a different perspective on how photonic platforms are being developed and applied, from really deep technical insights to industrial relevance and new paradigms in quantum information. Important to note is that after each talk, we'll open the floor for a brief Q&A session. So please feel free to submit your questions in the Zoom chat or on the YouTube comment box, because we would like to really have this session as interactive as possible. At QBN, we host sessions like this to really spotlight the great work of our valued members and to create opportunities for collaboration, dialogue, and discovery. And it's really about sharing what's real, what's next, and what's possible when we simply work together. So without further ado, and before we dive in further, I would like to quickly present you the agenda for today. So basically, I will start with a short introduction to QBN of who we are and what we are working towards. And then we'll move to our valued speakers. Each talk will be followed by a short 5-minute Q&A session, as previously mentioned. So as you're listening, feel free to drop your questions, and we'll try to really get as many of them as we can. Now, I would like to briefly present you the upcoming quantum leadership sessions. In the next few months, we'll be covering a range of topics, including quantum chips design and testing, how today's quantum hardware is being built and tested. This session is actually happening next week already, so don't miss it out. It's going to be really a fantastic one. The next one is quantum computers, where we are now, a clear look at the current state of quantum computing and what's working. And then quantum tech in healthcare, so real examples on how quantum technologies are being explored for use in medical research and diagnostics. If these really sound interesting to you, we would love to have you join us again. So each session brings in different people and new discussions, and we always try to really have the conversation practical and grounded. So if you enjoyed today's session and want to stay updated on the future quantum leadership sessions, please be sure to subscribe to our YouTube channel and register for the upcoming events on our QBN website to stay tuned for announcements and for any further important updates. So with that being said, I would like to move on to the quick QBN introduction and present you a little bit more information about our network. QBN was established in 2020 and brings together a diverse network of over 100 members, ranging from early stage startups and SMEs to large industry players and research institutions. Our members are active across quantum computing, sensing, communication, and cybersecurity. We basically work to strengthen the role of Europe and the Asia-Pacific region in the global quantum landscape, supporting innovation, security, and the practical use of quantum technologies, including really computing, sensing, and the quantum internet. But beyond really building connections, QBN also offers consultancy to help companies, investors, and public sector organizations understand and prepare for the opportunities and challenges of the quantum technology. We also support startups with hands-on guidance around scaling, go-to-market strategy, and attracting strategic investment. So that is QBN, the leading global industry network for quantum technologies. Our services are basically built around two main key pillars, the Global Innovation Network and Business Innovation Services. The Global Innovation Network focuses on topics such as policies, ecosystem, entrepreneurship, individual support, knowledge exchange, technological transfer and collaboration, and the provision of access to market, finance, and international business activities. The business and innovation services touches upon topics such as investors, end user industries, quantum industry startup, and investors. So in the next slides, you have a further breakdown of each of these pillars. This slide represents really our members. In just a few years, QBN has expanded significantly and now includes over 100 members from across the quantum ecosystem, basically ranging from hardware component makers to full stack quantum technology companies. And together they cover nearly every step of the value chain. So our network brings people together to tackle shared challenges, develop new business opportunities, speed up the journey from research to real-world quantum applications. So being part of QBN means really having a direct access to a strong community of experts, collaborators, and decision makers, an advantage in a field that's really evolving very, very quickly. So if you're curious about who is already part of the network or how QBN might support your work, I really warmly invite you to visit our website and explore what we are building together. Moving to the next slide, this one represents the membership. So basically, QBN is a global network that welcomes companies, research institutions, and organizations involved in the development of quantum technologies and their broader value chain. So again, joining QBN basically mean connecting you with an international community of professionals, from industry leaders and scientists to really investors and innovators who are all working towards turning quantum research into real-world impact and advancing adoption across sectors. So moving back to the key service pillars, the Global Innovation Network, I will start by matchmaking, through which we connect companies with the right collaboration and partnership partners within the quantum value chain. We also advocate for quantum technologies, guiding policy developments and creating a supportive environment through lobbying. And with access to both private and public funding, we leverage our deep tech investors and funding expertise to support companies' projects. Next is the technical working groups. We have 5 technical working groups which provide a platform for collaboration, knowledge exchange, and market insights across the value chain. QBN also really helps increase companies' visibility by promoting their product launches. And also we have the business forum, which offers professional knowledge and experience on critical topics like intellectual property, sales, marketing, and investment. So finally, access to our content hub and archive is readily available with industry reports, videos, and presentations to keep people informed on quantum topics. Then moving to the business and innovation services, basically our business strategy workshops help companies to unlock their business potential by addressing challenges and building on strengths to scale their operations. We also offer technical due diligence and investment advisory, aligning your strategy with the latest quantum trends and technologies. Next, QBN also offers and supports businesses use and case development, helping end users leverage quantum technologies in line with their strategy. We also assist with fundraising and partnerships, offering hands-on support in connecting you with investors and strategic partners. In addition, QBN enhances decision makers' awareness about quantum developments by developing and implementing effective communication strategies. Also, actually, our market studies and business intelligence provide tailored insights to guide data-driven decisions. And last but not least, we help our members explore new market and expand internationally with lean strategies and basically strong business support. On the next slide, I would like to also briefly talk about the quantum incubator. So the QBN incubator for end user enterprises supports companies looking to explore, but also to adopt quantum technologies by offering tailored guidance, mentorship, and access to the right expertise. So this program is really designed to help the end user businesses get started quickly and build a clear path towards their goals in the quantum space and environment. So as part of this, we offer also a fast track to quantum readiness that includes quick onboarding, a free enterprise membership only for the first year, and also a 25% of full QBN membership in that same period. So this, I would say, is really a great opportunities for those ready to take their first steps in the quantum field. So to learn more or to apply for this program, just really head over to our website and submit a membership request or simply contact us for more information. I would like to also very briefly present the QBN achievements. This slide really highlights how far QBN has come in just a few years. So we've built a growing international network of over 100 members, and really we have created a strong connections across the quantum community through events, partnerships, and joint initiatives. So thanks to this collaborative effort, QBN has helped really facilitate more than 200 million of euros in public and private funding, hosted conferences across the globe, and really steadily grown its reach now with over a 20K of reaching global presence in social media. So we've also established close working relationships with government bodies in Europe and beyond. Basically ensuring that the voices of our members are heard where policy decisions are made. Looking ahead, we are committed to helping shape long-term strategies, particularly in Germany, Europe, and the APAC region, to support the development of a strong, resilient quantum ecosystem by staying involved in policy discussions and basically engaging with decision makers. We aim to help guide national and international quantum agendas in a meaningful way. Here is a quick glance at the QBN team, which brings together really deep experience in both quantum technologies and broader deep tech fields, combined with a strong focus of company building, innovation, and network development. We work closely with our members, so basically offering support, insight, and hands-on guidance to help them grow, scale, and navigate the challenges that come um, with the development and applying of cutting-edge technologies such as the quantum technology. We also have a brief overview of the news from our network. I'm happy to introduce a few of our newest additions to our quantum community. The first one is Rax Consulting, which is also a founding APAC member, Twin Photonics, and Archimea. So we're excited to welcome them on board and really look forward to the work we'll do together in the future. Next, these are the events where you can meet QBN and the QBN team. I would like to highlight the ones where you would actually be able to meet the QBN team in person. So the first one is GTEx Europe, where we are a strategic partner of the Europe's largest tech event. So QBN will have a booth and will also host we'll be present at the booth. So if you're a QBN member, you're also eligible to get a 20% discount on the booth space through our partnership. So make sure to contact us for more information on that. We'll also be present on the World of Quantum, which will happen in Munich over the period of between 24th and the 27th of June. So there, once again, we will gather key players from the quantum field at our QBN pavilion, located really in a prime spot with high visibility and a comfortable lounge space. So this is really perfect for catching up networking, and kicking off really new collaborations. And also importantly, mark the date 25th of June in your calendars, where we'll be hosting our QBN VIP networking reception, which is a relaxed rooftop barbecue and drinks event. It's an only invite only. So yeah, this is an event where meaningful conversations and connections happened really in a relaxed and closed atmosphere. And last but not least, on the 23rd of June, just before the official start of the World of Quantum, the QBN Workgroup Photonic Quantum Technologies meeting will take place, hosted at AtoCube Systems in Munich, Germany. So I warmly encourage everyone to come and join us at this important event. So if you're planning to attend Berlin or Munich, we would love for you to stop by at our booth and connect with the team. And also one important note is actually the upcoming event, which is the fourth annual Commercializing Quantum Global, happening on the 13th and 14th of May in London. So me and our CEO, Johannes Vers, will be there present in London. So feel free to drop us a message if you would like to meet there as well. Here is just a brief list of the funding calls, which you may find valuable. They are currently open, and you're welcome to visit our website where you would be able to find more information. And with that, I would like to finish this presentation. If you're not yet a part of QBN and you're looking to get involved, we would love to welcome you into our quantum community. So basically, there are many ways for you to stay connected. You can follow us on LinkedIn, YouTube. You can subscribe to our newsletter, and also basically join us on our QBN portal. So yeah, this is an invitation to everyone. Let's work together to build a resilient and sustainable quantum economy together. And without further ado, I would like to move on to our talks. As I said, after each talk, we will have a Q&A session. So feel free to please drop your comments or questions in our chat. So with that, I would like to invite our first speaker, Benjamin Chicos, who is the quantum systems engineer at Photonics. He will walk us through the role of continuous variables in scaling photonic quantum computer. So yeah, Benjamin, the floor is all yours.
Thank you, Mila. Thank you for the introduction. And here we go. Can everyone see this? Good.
Yes.
Okay. Yeah. So good afternoon, everyone. My name is Benjamin Sichos. I'm a quantum systems engineer at Photonics, and it's a pleasure to be here today at the Quantum Business Network Leadership session. And I'd like to talk about quantum computing with photons, and specifically with continuous variables, and share how we at Photonics are working to make this reality. So, who are we? We are a startup based in Germany, and we have an ambitious vision of developing the first all-optical general-purpose processor. So it's not only including quantum, but it's just a new paradigm of doing computation, starting with a foundation in high-speed, efficient classical optical processing. And we're specifically focused on deterministic computing, so ensuring reliable and predictable operations. We leverage the natural advantages of light, so we have a high bandwidth and very low latency. And also very critically, our system is very energy efficient, which is a major concern for large-scale computing in the future. So where sort of does quantum come into this? So I've talked to you about what we do very briefly, but where is the quantum part of this optical processor? So we at Photonics, we envision a cross-domain processing unit, or XPU in short, where at its core we have an all-optical logical processing unit, where we utilize the fundamental speed and efficiency of light-based computing, where this is used for classical tasks. But these LPU is interfaced with reconfigurable functional units, or RFUs. These are specialized optical modules that are defined for that just do very specific tasks. So for some, this could be vector matrix multiplication accelerators, which are crucial for AI or machine learning, where optics can offer a significant speed up. Or another example would be a Fourier transform module, which is a very computationally intensive task on electronic processors, but in optics really excels at this sort of stuff. And most interestingly, in this for this context, is that one of these RFUs could be a quantum computing module. So this sort of architecture allows us to integrate quantum capabilities seamlessly into a classical processor where we can apply quantum advantage where it's needed and not so only where it's needed, and leverage the strength of all optical classical processing at the same time. So our strategy to define it in terms of an algorithm is, so we have this algorithm and we want to identify some key areas inside the algorithm where we can utilize quantum advantage to create some sort of speed up or optimize the task, which allows us to use this in the near term for specialized quantum simulators, optimization solvers for industrial tasks, or something like the traveling salesman problem, and also quantum machine learning algorithms. But in the long-term vision, of course, we want to create a large-scale universal fault-tolerant quantum computer. But the near term is what interests us at the minute more, because this is readily applicable in our general purpose optical processor. Now that I've answered sort of where quantum comes in photonics, why did we choose? What's so good about photons? Why do we want to use photons? And there's quite several compelling reasons, actually. So for one, this low decoherence of photons is very important. So photons interact weakly with their environment, meaning that we can maintain their quantum states for a longer period, which is very important if you have quantum computations which have very long depth. Secondly, we have this technology has a high potential for scalability, because we can leverage existing fabrication techniques that from telecommunications or the semiconductor industry to create photonic integrated chips on a very large scale. Then most easily seeable is that you just have high-speed transmission. So photons literally travel at the speed of light. So information just can be processed much quicker, read out much quicker. And for us, also very important is that we can use room temperature operation. So we have a significant advantage over other quantum modalities where you have complex and expensive cryogenic cooling systems. And in our case, this is not needed at all. So we can run our chip fully at room temperature, including our source and measurement. And we also have compatibility with existing infrastructure. I mean, communication nowadays is done via fiber optics, so why not have the chip being optic-based as well? There's no need for conversion between electronics and optics. It's much more energy efficient and simpler to convert everything to the optical modality. And finally, looking into the future, we have photons are just the natural choice for quantum communication and quantum networks as well. So by having a quantum computer that is made out of photons, we directly enable distributed quantum computing processors and secure communication between processors and also between different stations. So so there's some different paradigms in how you can use photons, and we at Photonics we use continuous variables. So this might be a bit of a new paradigm. So for us we have the qubits, which are the digital quantum bit for us, where you just have some discrete states and you have some superposition of these states. But there's also an analog counterpart, as I like to call it, which is just you have some continuous. You use the continuous properties of light, like the amplitude and phase, or the quadrature, so the x and p quadrature, and you with this, you open yourself to a whole, like to a lot more uh, options. And there's two key states that are very important to this continuous variable quantum computing paradigm, which are the coherent state, which is just so the light that is produced by a laser, where I've also shown here the phase space of two of these. So for a laser, this is just a circular blob that is limited by the Heisenberg uncertainty principle. And then also important is the squeeze state, where you squeeze one of the uncertainties in one of the quadratures, meaning you reduce the uncertainty in one of the quadratures, but which increases the uncertainty in another quadrature because you still have to satisfy the Heisenberg uncertainty principle. And these squeeze states is a very crucial non-classical resource that is used for continuous variable quantum computing. So, and now that we know what sort of what paradigm we use, what are the building blocks when you use continuous variables to realize continuous variable quantum computing. So quite easily, the first thing you need is, of course, a light source, which is a laser or an OPA, as shown here, which produces some squeezed light. Then, of course, you need to apply some operations on your lights. So the first you would do this with linear optics, which are some well-established technologies that can be readily integrated onto photonic chips nowadays. So you have a beam splitter or a phase shifter, which do some very basic operations, which you can cascade and finally do all linear operations that you would do on a quantum state. And then after your operation, of course, you want to measure your state. So this is usually done with a balanced homodyne detector, where your input state, so your quantum state is mixed with a strong classical source, a local oscillator, which and then is detected by two photodetectors. And the difference in the photocurrent just measures one of the light's quadratures of your continuous variable state. And then the tricky part of continuous variable state is the nonlinearities. So we need nonlinearities in continuous variable quantum computing to achieve universal quantum computing. So you need chi2, which is also an OPA, is also a chi2 nonlinearity, and you need the chi3 nonlinearity, which could be a de Coeur effect or for something like the cubic phase gate. And we need this to achieve universal quantum computing, and this is a major focus area to realize this on chip. And now these are all the building blocks that we need, and how does acatonics come into play? So what do we do? So we are focusing specifically on all optical measurement-based quantum computing. And in measurement-based quantum computing, the computation doesn't happen by evolving an input state through a fixed sequence of gates. Instead, we first have to prepare a large, highly entangled resource state, which is the known cluster state. And we can do this quite easily using in the photonic platform. So you would have two squeeze states, interfere them on a beam splitter to entangle them, and then you would delay one of them and then interfere them again, and then you would get a chain. And if you do repeat this, you would again get a 2D cluster state at the end, and then again you'll get a 3D cluster state. So this is the resource state is very important, and then what you then perform sequential single mode measurements on your resource state. So you have our input state here, which you interfere with some entangled state here, and you measure it, and the measurement is fed forward. And traditionally, in a conventional setup, this feed forward is done electronically. So the photodetector produces an electric signal, and this electric signal then drives an electrical optical modulator, which is then used for the feed forward process. But this is slow. So this process of the electrical feed forward is relatively slow compared to how fast light travels, and it can introduce latency, which often then requires that you have very, very long optical delay lines. So, and this ultimately limits the speed at which you can perform the operations, some gate operations. So what we want to do at Architectonics, we want to do an all optical gate. So specifically what we do is we replace our homodie measurement with just two another OPAs. Because in the high squeezing regime, so when your OPA is a very high gain, it approaches approximately closely your homodie measurement. So using this, we forgo the electrical stage completely, and our feed forward process becomes purely optical. And with this, we have much faster feed forward. We don't need these long delay lines, and we generally just can achieve very fast gate operations compared to the conventional electrical version. And currently, our research and development is at Architectonics is specifically channeled through these two projects. So we have our Spock project with our partners at Fraunhofer IZM and Noisy Labs, where we're currently designing the all-optical feed-forward gate. And the task is to package it and use existing technologies to create an integrated all-optical teleportation gate as well as the cubic phase gate. And then for more long-term, we are currently in a Mexico project with Fraunhofer IOF, XFAB, and Centec, where we try to develop very cost-effective components by putting nonlinear materials directly on silicon nitride and measure their active optical functions. This is just a very promising platform for photonic integrated circuits, where we hope to have these nonlinearities, so the Chi2 and Chi3 directly on chip. And yeah, and then finally, so what in the end, what do we need to do to scale up to make this an actual useful quantum computer? So for the measurement-based quantum computing paradigm, we need to be able to generate very large entangled cluster states. And this is done already by some research groups in Tokyo, where they've shown they can generate cluster states up to 1 million qmodes. And then you perform the computation on your cluster state by making sequential measurements of the entangled states in your cluster state, and feed forwarding your measurement results onto the next quantum state, pushing your computation through the cluster state. And then for scaling this, we want to be able to integrate this on a photonic chip where you can miniaturize the system and just produce it. We can use the semiconductor fabrication process to produce this on a large scale. And with the time domain multiplexing, or even frequency demultiplexing, we don't need so for generating large cluster states, we don't need a million OPAs or something. We can use even one, two, or just even one OPA to generate these cluster states by delaying one of these states, as I've shown earlier. So that's how we plan to scale up our quantum computing protocol. But there are, of course, some key challenges that we have to tackle first to make this a reality. So in the near term, what's very important for us is that we generate highly squeezed states. By generating highly squeezed states, we can lower the initial noise, and we can lower the error on our gate operations. and just improves how just improves the error on our gate operations, which is very useful in the near term and also in the long term, of course. And then of course, we want to minimize losses. This is always an issue with Photon, especially if you travel between chips. If your quantum state gets lost on the way, this is very bad, and we want to minimize the losses from edge coupling, so coupling into the chip and coupling between chips, which is very important. And as well, as I mentioned earlier, we need strong nonlinear interactions to achieve vital non-Gaussian operations that we need for universal quantum computing. And making these interactions strong and also be possible on chip is a very frontier research area currently. And in the long term, we want to be able to create something called GKP states, which is bosonic error correcting modes, where we can achieve fault-tolerant quantum computing, and we want to be able to fully integrate our quantum computer on a chip from the light source to the measurements using these OPAs, and this is our long-term goal. And then finally, giving a shout out to the amazing team at Photonics. So we deeply committed. So we have some we're very enthusiastic about photonic quantum computing, but also photonic computing in general. And we have two offices, one in Berlin, where I'm currently at, and also in Munich. And yeah, it's just very amazing to work there with some very smart people. And yeah, thank you very much. I'd be happy to take any questions as well now. And if you like to reach out, here I've attached the emails of our CEO and CTO.
Thank you, Benjamin, for that insightful overview and for showing us how continuous variable systems might help overcome key scaling challenges. I see one question in the YouTube comment section. So what is the difference between your technology and Xanadu's technology?
So Xanadu tried to do so they also use continuous variable quantum computing, yes, but they don't use this all optical feed forward. So that's what sets us apart. I think they recently published a paper right on in Nature where they've built everything together. And the key difference there is that they had, I don't know, almost 3 kilometers of delay line loops because they use this electrical feed forward instead of the all optical one.
Okay, thank you. Does anyone from our panelists have any questions? Yeah, Haitham?
Yeah, thank you very much for the great talk. I have one question regarding, looking into the future and maybe thinking about distributed quantum computing. And I know, let's say CV typically from QKD. So let's say either you have CV QKD or entanglement-based QKD. And I'm wondering if this, let's say, more naturally then goes in the direction of CV QKD if you want, for example, to have distributed quantum computing, or if you want to somehow, let's say, connect quantum computers. Can you comment on that?
You mean if CVQKD is more suited for our paradigm?
For example, if this more naturally, let's say, fits into that framework, or does it not matter? Or what's your opinion on that?
I think it's definitely CVQD perfectly fits into us. This would be just like I don't do too much on quantum cryptography themselves, but I think this would definitely work together very well.
Thank you.
Anyone else maybe having a question? I see one additional question in YouTube. So thank you for the very interesting presentation. Is there any reason why among the key states, Schrödinger cat states are absent?
Yes. So I just didn't include any nonlinear states. But of course, the Schrödinger cat state is very important, especially if you want to create the GKP, the GKP state in the end. Sorry.
Yeah, and additional question to this is, were you able to implement CV quantum Deutsch Jota? I'm not sure how to pronounce this. So one moment, I will write it down for you.
I think. No, so currently, so yeah, okay. Thank you for your question. Currently, we in the process of producing our first basically experimental implementation. So we've not done any experimental implementation for now. For the past year, we've trying to build up our theoretical foundations, and the first chip is about to be produced. Should arrive this May actually, or in June.
Okay, and one last question for you is, when you're dealing with quantum computing, do you observe phase collapse in light, where if you observe the quantum states of the chips collapse or affected, or are affected? So
I'm not.
yeah, maybe just 1 second.
Yeah.
We'll share the question here.
Oh, I'm not that sure, but maybe we'll be. So yeah, as I mentioned, we haven't done any experimental work yet. Hopefully, I can answer this next time I come.
Yeah, perfect. Okay, so thank you very much once again for this insightful presentation, and also for the very interactive Q&A session. With that, yeah, we can move to the next speaker. I'm very pleased to now introduce Dr. Thomas Volz, the Managing Director and CTO at Quandela Munich. He will share his perspective on how photonic quantum computers can deliver industrial advantages and speed up innovation. So welcome, Thomas.
Hi, everyone. First question, can you see my screen?
Yes.
Excellent. So I swap over to presentation mode. So, well, thanks, everyone, for coming to my talk. And thank you to QBN for for inviting me and giving me the opportunity to speak here. And to present Quandela and Quandela's photonic quantum computer technology. So let me start with just giving you a brief overview. So Quandela was first founded in 2017, based on 35 years of scientific research on semiconductor nanostructures and single photon sources. And it delivered its first commercial quantum device in 2018. We have now grown to over 100 people, 50 of which have 50 plus have a PhD in some topic, not restricted to physics. We have 2 production facilities in France, where we also have the headquarters, which is one of 4 main locations. We have the GmbH, Quandela GmbH, here in Munich, of which I'm the managing director and CTO. And I'll come back to that towards the end of my talk. And then we do have a subsidiary in Canada, and we're about to open one in South Korea. We have prominent scientists in Quandela. So there's, of course, one of the co-founders, Pascal Senela, who is part of the French Academy of Sciences, and also part of the advisory committee to President Macron. We have Alain Aspect, Nobel Prize winner, who is part of the scientific advisory committee. And we now, meanwhile, have about 40 patents and scientific articles coming out of Quandela. We are, and you would have noticed that in the video that I was showing, we are a full stack provider. We do everything from hardware manufacturing to assembling our own quantum processes, providing an own open source programming framework. We develop quantum algorithms together with industrial clients. And we also have a cloud offering where you can access our QPUs on site. So we built our hardware, I said that already. So we have a quantum computing factory where we assemble the optical parts. And we also have a quantum data center where once the quantum computers are assembled, they're wheeled in there, connected up to the internet, and people can actually access these quantum computers from the outside through the cloud. We also have our own semiconductor qubit device fabrication line, which sounds complicated, which is nothing but a production line for fabricating single photon sources. And we work with partner semiconductor foundries on the photonic chips, and I'll come back to that. But of course, the key technology that Quandela is famous for, and also originally famous for, and was built on, you can see in this micrograph up here. So this is actually a micropillar structure which is carved out of a gallium arsenide wafer, and there is a quantum dot located right at the heart of the cross here. And once you excite the quantum dot with laser pulses, you get single photons out. This is again shown here, but this time in a bit more detail. So what you see here is such a micropillar structure, such a single photon source with a quantum dot right at the center. You see nicely the grown DBR mirrors, bottom and top mirror of the cavity structure, the cavity spacer here. And you see clearly that the bottom mirror has many more pairs, DBR pairs, than the top mirror. So meaning that whenever you excite the quantum dot, the light, the photon is emitted through the top. And with that, we can actually deterministically generate single photons. Quandela's single photon sources are best in class. They have really great indistinguishability, which is key for the photonic quantum computing I'm going to talk about in a moment. The technology, of course, we've heard that in the previous talk, semiconductor and photonics are nice platforms or nice key technologies that are in principle scalable. We have coherent control over our quantum dots, which is key, which enables us to ultimately use the spin of the quantum dot to not only have the photons come out one by one, but also generate entanglement at the source. So we can essentially drive the quantum dot in such a way that there is spin-photon entanglement and photon-photon entanglement, so we can generate cluster states on demand. All right, this is, let me jump back a few years. So right from the start, I mentioned 2018, the first device was delivered, and this is typically what you get when you order a single photon source from Quandela. So it comes in a nice rack. This was enabled by, so we need to cool the quantum dots. So you need a cryostat, typically 4 Kelvin or a bit below, which also means you need a compressor. And we have a long-standing partnership with Atocube, who developed their new igloo quantum compressor, and which allowed us to ultimately pack everything into one rack and have it essentially wall plug ready. And the important part on this, and so what you can see here, this spaceship looking like structure here is actually let me just get also the laser pointer. It's easier. So this spaceship like looking structure is actually a single photon source, which is pigtailed to a single mode fiber. The important point here is that since 2017, there have been many articles coming out of academic labs that have been generated with Quandela single photon source technology. So how do you do computations? So this is shown here. So you have your single photon source. You take your single photons. You have a demultiplexer, and you do synchronization such that the photons, instead of arriving one after the other, arrive simultaneously at this photonic chip here. You've got this 12 by 12 chip here. So 12 input, 12 output ports, which consists of a mesh of Mach-Zehnder interferometers, which are all controllable with phase shifters, thermal phase shifters in this case. Once the photons propagate through, you detect them with single photon detectors, and the output, of course, is your result of the calculation. And as we heard in the previous talk, the nice thing about these photonic chips is because photons are robust to noise, they don't decohere, that you can send them through a room temperature chip and it's not a problem. And so the photonic chip itself is at room temperature, except the detectors and the single photon source are at typically 2 Kelvin. Because of the high repetition rate of the single photon source, this modality is high speed. We get high precision by having many repetitions. And as I said, photons are robust to noise. Only problem is sometimes they get lost. And I'll come back to that later. Okay. Now, the first photonic quantum processor that was available in the cloud happened in 2022. Paper was published in 2024. It's essentially the same architecture that I've just mentioned. So you've got your single photon source, you've got the demultiplexer, your photons arrive at your universal interferometer. Nice thing, once you've got a universal interferometer, you can generate any unitary. And what essentially this does, if you just work in the modality that I've mentioned before and use it in the boson, so-called boson sampling mode, then you just simply get the permanent of that matrix as a result of your calculation. You detect the photons once they pass through the chips with SNSPDs. Typically, you've got the correlator. The correlator is read out with a classical machine. And as I mentioned before, in principle, you can access the machine via the cloud, via Quandella's own cloud platform. And Percival here, this horse here, indicates Percival, the open source framework. Now, this is how it all started in 2022. Literally, the whole experiment was in the lab, and then 1 year later, it was packaged and delivered to a customer, to AVH Cloud in late 2023. So this is how it comes. It really literally is wheeled into a data center, plugged into the wall, and more or less works. So the upshot of that is that we already deploy quantum computers to industrial customers. There's OVH Cloud, Exion, it's got a machine. There is a machine to be delivered within the context of the Euro HPC initiative. Later this year, a 12-qubit machine. We have deployed about 4 systems over the past 20 months. And you can easily, as I mentioned, integrate that directly into the HPC environment. It's resilient and low energy. I should again highlight that of course, it's not enough to have hardware. You also need a software framework, and we have the Percival framework that is adapted specifically also to the peculiarities of photonic quantum processing. What we also do besides hardware and the software, we also develop quantum algorithms. So we look at the application side of things. We have a applications and algo team, which work with corporate clients. Some of them are listed here, to develop software solutions together for their problems. Okay, and I'll go back. I'll come back to that in a moment. I should highlight that we have a specific program. This is in the end, it's a commercial offering as well, but that's called the Quantum Acceleration Program, which sort of lays out the steps that are taken together with interested clients from industry to work through their problems with Quandela solutions. There is also, and just highlight that here. So we've got our own cloud. As I said, we've got more than 1,000 users now. Many QPU seconds that have been used by external users. It's divided up in 3 parts. There is a hub, which is essentially you can exchange with other users and you can explore solutions. There's a training center where you can learn about photonic quantum computing, how it works, what you can do. And there is of course the cloud itself, which gives access to the online QPUs. And you can also have GPU enhanced simulators to run simulations rather than directly do your calculations on the hardware, the photonic hardware. Now, here are some examples of the use cases that we currently have. There's a lot sitting at the interface between quantum and AI. The clients are listed here. These applications are typically finance, chemistry, and also aerospace. I'm going to talk a little bit about that in a moment. These are, as I said, in the AI space, or adjacent to AI. Whereas what you see on the right-hand side is more or less based on variational quantum algorithms. And this last application I'm also going to talk a little bit about in a moment. It's more on the cybersecurity side. Okay, so I think it's safe to say that we're quite fond of this one. This was actually a competition that BMW and Airbus announced. A global competition that we won. We won one of the category, the hybrid quantum AI category. And what this category was about was to, within this challenge, was to translate real images to nighttime images. And Quandela proposed two different approaches, one based a pure quantum approach, where instead of taking the classical approach to generation of nighttime images, a classical GAN approach, you replace the intermediate steps between an encoder and a decoder just with a quantum transformation or quantum annotation, and that sort of already does the job. You don't need to do extensive training. It cuts down on your cost. It cuts down on the time it takes. But as you can see on the right-hand side here, there is still room for improvement in terms of the output. But that's certainly one way to go, and Quandela proved that it's possible. On the other hand, the second solution that Quandela proposed was and implemented was to combine the classical GAN with boson sampling, so the photonic computer, quantum computing, and to generate the images, and that significantly reduced hallucinations. And Quandela was able to prove that and show that, and that in the end, I guess, made the contribution win in the end. So, so yeah, that's one example of the kind of applications we're looking into. Then a bit of an older, one of the first applications that's in connection with the first delivered quantum processors to the OVH Cloud Data Center in 2023. And the goal of the project was just to protect their data against any attacks via quantum algorithm. And so the idea was, well, we deploy a QPU and we implement a quantum random number generation protocol. And that way we can generate cryptographic keys on site from quantum random numbers, certified quantum random numbers, and that in the end gives the ultimate level of security. Okay, so this brings me to an overview of kind of the applications that we're currently seeing and that we have in mind long-term. So at the moment, in the 2023 to 2025 phase, well, I just talked about cybersecurity and quantum and AI, and that's very active, and there's a lot of activity there. We will also have our own AI platform and interface that's, I think it's about to be deployed, or has been announced at least already. There is then the second phase, the scale up and scale out phase, where we see other applications in energy specifically, infrastructure maintenance, energy grid optimization, and quantum chemistry. And ultimately, beyond 2029, we're looking at the applications in healthcare and energy, things like battery design, catalyst design. But of course, there is an issue here, and for those of you more familiar with photonic quantum computing would have noticed, with the kind of proposed technology, or the technology I've talked about so far, this is not so easily possible. This is too sort of compute intensive, these kind of applications, that you actually need to go to large scale computers and you need to go to fault tolerance. And the question is, how do you do that? So here's the roadmap, and we've written up that roadmap. You can download it on the web as well. So here we started out the 6-qubit machine. I've talked a bit about that. We're currently at the 12-qubit stage. We're looking at 24 qubits, 48, and so forth. It's safe to say, or it's just a side remark. Turns out that once you've got 40 photons, typically, then you will not be able to classically simulate what's going on. And that means we expect some quantum advantage here at some point, and utility. But long term, we're looking at fault tolerant architecture. And for that, we have come up to where we use sort of these kind of research states or cluster states to generate resource states. And that's called a Spock architecture. And this is where it is. So one of the key issues in the conventional way we do, that I talked about before, that we do photonic quantum computing, is the fact that once you scale up your chips to more and more photons, of course, even if your losses are very, very small, if you have many channels, you're going to lose, and it's hard to really scale up to beyond 100 qubits. So how do we go beyond that? Well, here is the idea. So the idea is to use both the photonic degrees of freedom, but also the spin degrees of freedom of your quantum dots. So really have a hybrid like matter qubit approach where you use many photon sources, okay, the quantum dot spins. You have, and in turn, that's the price you pay, but in turn, you can reduce the complexity of your photonic architecture and your photonic chips. You essentially have routers, which will have fast switching. And then you have these 4x4 chips, which implement a RUS gate, which is a repeat until success gate for generating the entanglement. And with this, this is the basic module, but you can scale up this to many, many modules and connect them all up. And the system or the architecture is inherently, and our technology is inherently modular. So it's an easy way to scale up. And the key is that in order to scale up efficiently, all you need to do is you need to optimize your one module. Once you have reached a certain threshold for that one module, you're fine to go and you can hook them all up. And we actually compared the architecture, Quandela's architecture, hybrid architecture, which uses the light and the matter qubits, with pure photonic competitors. Of course, the competitors in the single photon quantum computing space that go a different way, that don't use single photon sources, deterministic single photon sources, but parametric down conversion. And there you can do the numbers, and you see that in order to generate one such resource state, as is shown here, you need many, many more sources, detectors, phase shifters, and so forth. And you also have less of an fault tolerance or loss tolerance, so to speak. Whereas in our case, what we find is that to generate one such resource state, you need 12 sources, 24 detectors, 24 phase shifters. And at the moment, at least, and we're working on that to increase this number in terms of loss tolerance, you can allow yourself 4% losses in your system end to end, and it still works. So once you've optimized your one module to 4% loss or below, you're fine to go and you can scale up. And so that this is, you can check that it's the hybrid solution that we have at Quandela is 100,000 times more efficient. But of course, we're not there yet. And so one key is to have the production that we have, the quantum computer assembly also, and all the components ready for scaling, okay? And that's kind of the next step that we've been taking and that we're taking now. So here you see kind of what the ingredients are. So we have our qubit generator, which is a single photon source, which we're continuously improving in-house. We have the processor unit. We design the chips ourselves. We go to foundries and order those chips there, high quality foundries. We have the optical interconnects and we have the detectors, and everything is very modular and interconnected, which is a really big advantage. So you can buy the best components from different providers and put them together. And moreover, again, we're talking photonic integrated circuits, high quality foundries, and we have high quality semiconductor processes as well at our disposal. So just a few words and then I'm almost done. We have a semiconductor pilot production line. So we opened a clean room last year in Massy, our own clean room, where we do in situ lithography of our, as a first step in the fabrication of the single photon sources. We do etching of the nanostructures, we do the characterization and the fiber pigtailing all in one clean room. And that allows us to have redundancy in all steps, process reliability. We're looking to increase our yield of the good single photon sources, the production rate, the quality, and the reliability. And that's all housed in this building. This is a research institute for solar cells, but as I said, we've got our own clean room in there. So and here comes the kind of a little advertisement for the Quandela GmbH in Munich. So at the moment, we have access to a molecular beam epitaxy machine for growing the semiconductor wafers at C2N in Paris or in Massy. But we don't have an own MBE machine, and that's about to change. That's what Quandela GmbH was founded for, really, to build up a semiconductor R&D hub with specific focus on semiconductor growth. But of course, we're also going to be active and looking for customers, industries that want to use Quandella's technology and develop quantum algorithms for their problems together with the local quantum algorithms team. And so with that, I finish with sort of the mission statement and with a list of all our supporters. And thank you very much for your attention.
Thank you, Thomas, for your valuable insights and for showing how photonic platforms are already making their way into practical use cases. Let me have a quick look for any open questions. Okay, so there is one question in the YouTube comment box. So since you're generating non-Gaussian states, fog, then how do you minimize dissipation, scattering effects to maintain non-Gaussianity? Sorry for my pronunciation. Which algorithms do you use to minimize errors?
These were 3 questions, but one thing is to minimize. I assume this is what's meant. So you create single photon states and you send them through your chip. So you need to minimize losses. If that's what's meant, please correct me. You just minimize your losses in the system. What was the second question? Sorry.
So which algorithms do you use to minimize errors?
Okay. So we have some error mitigation techniques that we use to sort of make use of non-optimal photon detection events. So we let's say you wanna use 6 photon events at the end of your chip, but you can also make use of if you only see 5 clicks, you can actually mitigate your errors. So there's a number of error mitigation techniques. I can also post some papers on that or some references for that. But that's one way. And then the new technology or the new platform, the new Spock architecture lends itself to all sorts of. Actually, it's compatible with all sorts of error correction techniques. And so that's all laid out in the Spock paper where the architecture is introduced.
Mm-hmm. Okay, so thank you very much for this answer. Does anyone from our panelists have any question? Yeah, Haysam?
Yeah, thanks again for the talk. I have one question. So in your experience, which industries are currently most ready to benefit from photonic quantum computer, and what kind of problems are they typically asking for?
Typically, there's some photon native algorithms where you, for example, graph problems or dense subgraph problems, some optimization problems. So we've got clients, for example, SNCF is a client to optimize their train network. Logistics is an interesting one. We have a use case where we worked with forgot which company that was, provider in France. Finance institution, where they looked at portfolio optimization and looked at kind of optimizing the prediction of fallen angels. We were able to show that the quantum solution was slightly better than the classical one. And of course, even a few percent make a big difference because it's effectively money that is saved on there. So that's another one. So then of course, very big at the moment is quantum and AI, generally speaking, where you do classification and you combine techniques from AI and quantum, and that can be applied across very different sectors.
Thank you very much. And then I have maybe one more question, a little bit going again in the direction of end users and industry users. So what would you say are the biggest challenges that they are facing? So when, let's say, an industry end user comes to you, so what are the main challenges do they have? Like understanding quantum, because you mentioned also this quantum acceleration program. So this seems to be something that is especially addressing them. So what are currently the biggest challenges to convince them or maybe to work with them?
Well, so of course, at the moment, it's at the moment the situation is this: you work with the end users to define problems and identify problems where quantum could help. You develop algorithms, and of course, at this stage, with the number of photons we have, you can simulate things, right? You can classically simulate the outcomes. But of course, once you reach a certain size in your hardware, then the quantum hardware will bring an advantage and a utility to the customer. And so getting them to understand that and working with them from day one and lowering that barrier of understanding, as you say, but also you want to make sure that they understand the value that it can bring. So it's really an education and an engagement and a conversation in the end, right? It's an invitation conversation, and the nice thing is, obviously, the QIP program is going well. We have recurring customers there, so it's companies that said, yes, we like your offering, we've got good experience, we take the next step with you. And of course, it's about building that pipeline and sort of developing that long-term engagement with the users.
Thank you very much.
Thank you very much. Does anyone else have any further questions? There are no more questions in the comment box here. I don't see any hand raised. So with that, thank you once again, Thomas, for your insightful talk. We can now move to our final speaker for today, who is Roberto Siagri, the CEO of Photonium. He will present a fascinating approach to photonic quantum systems through the lens of qudits, so using more than 2 levels to encode information. Welcome, Roberto.
Thank you. Let me start. So I will go through this subject. Yes, multidimensional qubit or qudit with photons. This is a sort of topology, using the topology of photons to do computation, what it is also called twisted light. During this presentation, I will go through these 5 arguments. Our vision, photon as qudits and gate-based quantum logic and topological error handling, and what we are doing now, our circuits, the circuit that we are playing with in this moment. So this journey started with the concept of edge quantum processor. Instead to look at the centralized big quantum computer, we have figured out how to design small edge node, quantum edge node, that are in some way capable to operate at room temperature. Of course, they must be compact, and they have also the other feature to be scalable. And of course, because they are at the edge, they have to be low power, and they also to be able to operate in harsh environment. So in this way, the plan is to be able to install this quantum processor in satellite, airplane, tower station, or train, or whatever that is on land or the space. And this approach means that we have think how to miniaturize this quantum processor unit in a way that can be combined with standard classical computers, a sort of accelerator. So as you have a GPU, why not to have a QPU? And we envision 3 form factor as a chip, as a desktop unit, or as a PCIe add-on card. So that's the 3 form factor that we are looking to. Some of the story about photon was already explained by the previous speaker. Matter of fact, yes, photon are quantum at room temperature and has offer low decoherence. And but what we are trying now to leverage of the photons is a special properties of photon that is the orbital angular momentum. And why the orbital angular momentum? Because the orbital angular momentum is naturally multidimensional. And it offers an infinite state space, and so you can scale the encoding. And out of the orbital angular momentum, we can explore qudits, so higher dimensional qubit. And all these things started from the investigation from our CTO, Fabrizio Tamburini, that is an expert on this orbital angular momentum. And one of his work, it's especially on how you can manage the orbital angular momentum as a quasi-particle. And if you can manage the orbital angular momentum as a quasi-particle, you can have many qubits inside a single photon. So that's the idea. And because of this, the advantage is that not only they are robust, and just for how Fabrizio started this whole work was looking at the astrophysics problem and analyzing that photons that are coming from the outer space in some way embed these characteristics. And if they are traveling many light years in time, they should be robust. They must be robust. And this is one interesting thing. And they are robust. They are at room temperatures like photons, and they are part of the photons, and they can represent more than one qubit inside a photon. And just for explain what it is, we are normally used to see the photon as a spin angular momentum, as the component of spin angular momentum. And sometimes we forgot that there is also another things on the total angular momentum of photon, that is the orbital angular momentum. And combining these two, the spin orbital angular momentum and the orbital angular momentum, you can have at least as minimum 2 qubits. And because of this, you can start to think that you can do some deterministic gate, 2 qubit deterministic gates with the same photon. And as everyone know, one of the challenge in photonics is to let the photons interact one with the other. In this way, we use the auto-entanglement of the photon, and the photon perform these gates with his own states, his own orbital angular momentum states. And this is one big step ahead in simplifying the design of a universal quantum circuit, and playing with orbital angular momentum and path and time and spin angular momentum, we can design a lot of gates, a lot of quantum circuit in a new way, in a more simple way than before. And so what's happened is the following. You can have a waveguide that is carrying 1 photon, and the 1 photon has 4 states. This is an example how you can implement the circuit. And using this QQuart, you can figure out that you can implement a CNOT, an Hadamard, Toffoli, and so on. So because it is deterministic, you do not need any post-selection. And it can be implemented using a linear optical element like the Mach-Zehnder or other phase shifter and so on. So and then how we look at the problem of the error correction. We just look at the problem of error detection, and we have again another methodology that in some way is able to figure out if there is a mode mismatch, And if there is a mode mismatch, we can repeat the measurement, the experiment. And in this way, we do not have to collapse the qudit. And it is just a symmetry mismatch. And in this way, we can repeat, and we do not have to correct. We just repeat. In order to implement this, we need very high frequency single source, photon single source, and that's what we are also working in order to increase the frequency of the photons. And this is the two chips that we have developed up to now. One was designed at the end of 2023. Well, the company, I have not said that we started in March 2022. So on the end of 2023, we have developed the first silicon to validate the building blocks, the logic that I have described before. And now we have just received a new chip that is a little bit more complicated than the first. And with this one, now we are running some algorithms, and this is a 4-qubit, is a 4-qubit chip. And the setup is very simple. It is all at room temperature. You need just 5 detectors, a time tagger, and the photons in a single photon source, and this is the setup. So as you can imagine, this is also easier to miniaturize compared to other kind of setup. That said, the chip is there, and it's the one that I have shown before. Just to summarize what we are doing with this multidimensional qubit, we are doing something that is very energy efficient. Of course, it is also compact. We are using standard silicon photonics processes, so it is scalable. Well, we envision to connect together all these kind of small edge processor, and they are, of course, also fiber compatible. The reliability is in the simple circuit and in the photonic single photon approach. And we do not need entanglement for the logic. Of course, we use entanglement, but not to perform the logic, because we use the auto entanglement of the photons. And that's the presentation.
Thank you. Thank you very much. Just let me have a quick look in the comment sections. So what type of single photon source are you using? I believe this question is for you.
At this moment, we are using a commercial off-the-shelf single photon source that is of course, is an entanglement photon source with 2 photons, one that is used as an heralded photon, and one is entering in the circuit. And we are developing our own source in order to increase the frequency. We aim to be able to design something that has to be in the couple of 100 megahertz, 500 megahertz repetition rate of the source. And we will receive our first design in September, October of this year. So we should be able to have our own source by the end of the year. And at this stage, we have run all this chip at 1,500 nanometer is a telecom frequency. but in the next generation product will be at 800 nanometer and silicon nitride and not silicon. So we have started with this traditional telecom stuff just because it was much easier just to prove our theoretical foundation of this multi-state qudit, and but then we are moving on silicon nitride, and the generator will be on silicon nitride inside with the processor, together with the processor.
Thank you. There's, I think, in addition to this question, so sporadic down conversion or quantum dots?
No. It's sporadic, and we do not need. Well, we do not. The point is, in order to keep everything at room temperature, we cannot now use quantum dot. So we use and for the frequency. There are two main questions: the frequency of the generation, for how our algorithm in the error correction, that is more a detection and repeat. For a detection and repeat strategy, we need a very high frequency. And the fact that it's sporadic is not at this moment a real constraint. Of course, if it is deterministic, it's much better, for sure. But our goal is to be everything at room temperature and small. So that was our initial constraints. So we started from the constraints, not from the quantum computer. So we say that's the constraints. We have to fit inside these constraints.
Okay, perfect. Thank you so much. There's one more question for you. So could you elaborate on what kind of exotic symmetries are you looking for? How can exotic symmetries bring value advantage to quantum computations?
Well, the point is that this is the symmetries inside the photon. So the photon itself, it's a very complicated object. And if you're looking at the symmetries that you have with the quasi-particle symmetries, basically, that the orbital angular momentum is a way can be analyzed in quantum mechanics and can be transformed in a quasi-particle, and this quasi-particle has these symmetries that let you to do quantum computation. So it's the article that I have presented before. If someone is really interested, they can just check this article on the Fabrizio on Majorana bosonic quasi-particle for twisted photon in free space, and here he can find out and we will soon release in a couple of weeks another theoretical article that explain all this computer from starting from the theory up to the correction, and so it's everything will be published very soon.
Perfect. Thank you so much. Haysam?
Yeah, thank you very much for the great talk. I have one question regarding the higher order states. So if I understood it correct, you're using, let's say, OIM and SEM combined.
Yes.
Why not using, for example, higher order OIM beams?
Well,
just to say higher. For both.
Great question. We are looking for, but it's not in a free space. You can use many level of OIM. So you can use L1, L2, L3, L4, L5. When you constrain this photon in a waveguide, it's tricky. Yes, of course, it's a good argument for the new exploration in terms of production, manufacturing, and just to move. Now we are happy with the L1 and -1, but of course, at least L2 and -2 should be possible. And for sure, in open space, this is not a problem. But you have to consider that you have to put this kind of photon in a cage, in some way, in a waveguide. And just to design the waveguide is a big challenge. Is a process, depends on the process, the manufacturing process, and depends also on a lot of the precision of the process and how you design the waveguide. You cannot turn very fast when you carry these multimode things. The geometry is not easy, as there needs a lot of simulation, But of course, you are right. Why not? But we do not envision more than two, L1, L2. And but I think that is enough. We are thinking about dozen of qubits, not 100 or 1000 at this stage. And then we want to leverage the quantum network to connect this. So to have a lot of building block with dozen of qubits, all quantum connected with a quantum internet.
Okay, I see. So let's say having higher order OIM waveguides, let's say where the eigenmodes are also matching, is difficult to fabricate.
Yes,
basically.
yes.
Okay. And could you have them maybe like something like, let's say, photonic crystals or photonic lattices where you can have then that kind of structures? Because there you can have, I think, higher order modes as eigenstates from the lattice itself.
Yeah, but well, yeah, at this stage, just because we are really focused on having all this running on few qubits in, say, 10, 15, 20 qubits, we play with the L1 and -1, L0 with the sum. So at this stage, and then we have also path entanglement that can increase the number of qubits. So we have many ways to increase the number of qubits at the level that we want to be in 2027, and then we will see the next. Yep, everyone want to use more than one L, of course. So we really like to be able to do that.
Yeah. And then maybe one follow-up question. I didn't fully understood what is, let's say, the medium where the interaction is happening. So are you using, let's say, any kind of nonlinear crystal or something? So because you said, let's say, you need to have interaction between the modes, or let's say the qubits or qudits.
No, the qubit, because it is an auto-entanglement, is the photon itself that interact with itself. Because this orbital angular momentum is a property of the photon, it is like, in theory, you can in the free space, you can embed an infinite number of qubits inside one single photon, theoretically speaking. So we just embedded more than one. So we have two qubits inside the same photon. And because it is inside the same photon, they are auto-entangled. So you do not have to entangle, because the problem of the two qubit gate is that the two photon has to interact, and that is non-deterministic. But if you use the auto-entanglement of the photon, this is deterministic. So we have the two qubit gates that are deterministic.
Okay, thank you.
Thank you. Thank you, Roberto, very much for that thought-provoking presentation and for opening up new dimensions in quantum information. This was very insightful, and thank you all very much for the interactive Q&A session. I think that this was also very valuable for everyone. So I would say that this brings us to the very end of today's quantum leadership session on photonic quantum technologies. I would like to say a huge thank you to our speakers, to all of them for sharing their expertise and really giving us a closer look to how photonic quantum technologies are evolving. Of course, thank you very much for all of those who joined us as well, whether you were on Zoom with us or watching us live on YouTube. Your questions and participation make these discussions more valuable, and we appreciate you being part of the conversation. Once again, if you would like to stay connected, here is a quick overview of how you can follow us on LinkedIn and YouTube for updates on upcoming sessions, industry news, and job opportunities. Make sure to also subscribe to our newsletter to access more QLS sessions on demand and really stay informed about new events and updates from our community. And if you would like to be more involved, also consider joining the QBN portal. It's a great way to connect with others from the QBN members. And we are basically working toward the same goal, so building a strong, sustainable quantum economy. And our belief is that the more we collaborate, the faster we move forward. So thank you very much once again, and we hope to see you at our next quantum leadership session. And hereby, I would like to also wish everyone a wonderful afternoon.
Thank you.
Thank you. Bye-bye.
Thank you for the
Thank you.
moderation.
Thanks.
Thank you.
Bye
See
bye.
you. Bye.
Bye.